Hello everybody. Today I'll be talking to you about the reaction that you'll be doing in lab this week, which is the nitration of methyl benzoate. You can see the reaction scheme here, reacting methyl benzoate with nitric acid and sulfuric acid to get your product. Before we begin, there are some brief safety considerations. Nitric acid and sulfuric acid are both strong acids and should be handled carefully. Both are corrosive and will burn you if left on your skin. Make sure to wash any affected areas with copious amounts of water if any does get on your skin. Additionally, nitric acid is a strong oxidizing agent and will react very strongly with organic compounds, so make sure to wash any glassware that contain nitric acid with water before trying to clean it with other solvents. If any acid is spilled in the course of the lab, make sure to neutralize the spill with sodium bicarb before attempting to clean it. The type of reaction that you'll be doing in this lab is called electrophilic aromatic substitution. Electrophilic aromatic substitution is a reaction that involves the replacement of a hydrogen on an aromatic ring by an electrophile. Due to the fact that we are breaking the aromaticity of the ring, strong electrophiles are necessary for this substitution to take place. In electrophilic aromatic substitution, substituents that are already on the ring will have an effect on where the electrophile will be located after the reaction. Groups on the ring can either be ortho-para-directing or meta-directing. The image on the right shows the positioning of ortho, meta, para relative to the R group located on the ring. On this slide, we have examples of both ortho-para directors and meta directors. Now, how these directing groups work has to do with resonance. Ortho-para groups are electron donating groups, which donate electrons into the pi system of the aromatic ring, and meta directors are electron withdrawing groups that remove electrons from the pi system of the aromatic ring. If we follow through with the bottom image, we have an example of this using a meta-director, the nitronium ion. So if we follow this, when the nitronium ion is added in the para position, we get a positive charge on an adjacent carbon, which if we then go through the resonance forms by moving electrons around, and we get the second resonance form, we can see that the positive charge is now adjacent to a partially positive carbon, leading to an unfavorable interaction that is unstable because we have like charges next to each other. By contrast, with nitronium ion in the meta position, these charges are further away from one another as we go through the resonance structures, minimizing any electron deficiency and minimizing those like charges being next to one another, which leads to the meta product being the favored product. The first thing we do in this reaction is the generation of our electrophile, in this case the nitronium ion. To do this, concentrated sulfuric acid is added to concentrated nitric acid, which generates the nitronium ion through dehydration of the nitric acid. Now, between sulfuric acid and nitric acid, which is the stronger acid, and how does that cause this reaction to proceed? Sulfuric acid is the stronger acid, which allows nitric acid to be protonated, which generates our nucleophile. For the procedure, you'll start by adding concentrated sulfuric acid to an Erlenmeyer flask and cooling that in an ice bath to 0 degrees Celsius, followed by the addition of methyl benzoate. After this, using an ice salt bath to cool it again to 0 degrees Celsius, you will very slowly add a 50-50 mixture of concentrated nitric acid and sulfuric acid. You will want to keep this mixture stirring continuously during the addition, and make sure to keep the temperature below 15 degrees Celsius, or else the formation of unwanted byproducts greatly increases. After all the acid has been added, allow the solution to warm to room temperature. After the solution has warmed to room temperature, pour the mixture over crushed ice. After the ice is melted, filter the product using a Buchner funnel and wash with cold water. Following the water wash, recrystallize the product from methanol and determine the percent yield. Lastly, determine the melting point of your product.